Hello everyone, myself Yadagiri, Assistant Professor, Department of Electrical and Electronics Engineering, MLR Institute of Technology, Hyderabad. So in this session, we are going to discuss about the procedure about the Norton theorem and also the applications of the Norton theorem. So in this session, we need to discuss about what is Norton theorem. So where we need to use a Norton theorem and what kind of applications are there for Norton theorem. So these many things we have discussed in this session. So now we need to discuss about the first of all statement of the Norton theorem. So the Norton theorem is also the network theorem which is used to applicable for the complex network to get the response quickly. So that is the purpose of the network theorem. That is Norton's theorem. So it states that in any linear two-terminal bilateral network consisting of the more number of active elements and the more number of passive elements. So this is the more number of passive elements. The whole network can be simply replaced by an equivalent circuit consisting of the single current source that is called Norton's current. So which is parallel to the single resistance that's called Norton resistance. So this is the simple statement of the Norton's theorem. So again we are elaborating the theorem Norton's theorem statement, that is it simply states that in any linear bilateral two-terminal network consisting of the more number of active elements and the more number of the passive elements. So the whole circuit can be replaced by an equivalent circuit consisting of the single current source which parallel to the single resistance, that's called Norton resistance, and corresponding current is called simply Norton's current. So this is the given network. So the whole network we can simply replace it by the single source network. So that is the procedure given by the simply Norton's theorem. So let us take a simple network. So we need to we need to discuss about the Norton's theorem. Norton's equivalent. How can we get the Norton's equivalent by the simple network? So for that reason, we can consider a simple network. So this network having the many elements like active elements and also the passive elements. So in this theorem, so if you are able to determine the network from this state to this state, so we can simply go through the calculation of the Norton's current and also the Norton's resistance. So by determining these two Norton's parameters, we can simply replace with the any kind of complex network into the simple Norton's equivalent circuit. So simply we need to go through the one example. This is the one example. So the whole circuit simply replaced by, so the entire network or circuit can be replaced by a single current source, and which is in parallel to the a single resistance. So hence this kind of network is called Norton's equivalent network. So this is the procedure we need to follow to get this kind of network, single source network. So for first we need to discuss about the how do we get the Norton's current value. Norton's current parameter, this one. So while calculating the Norton's current, while calculating the Norton's current of the network, so we need to simply remove the load resistor. So in any kind of network, so from there we need to get the IN value. Simply we need to remove the load resistor. So whatever the element we need to calculate the required parameter, that is a voltage, current, and the remaining things. So that element considered as a load element. So we can simply remove the load element from the load terminals, and which can be simply short circuited. So this is the short circuit path we have provided. So instead of the load. So this is a given network. So from this one, we have to remove the load resistor from the load terminals, and the corresponding terminals are going to be appear like this. Means the corresponding terminals are going to be appear like this. So simply we can close this terminal. That's called short circuit by the load terminals. So this is the procedure to get the IN value. So how do we get the IN value means? So from any network, simply we need to get the IL value. We can remove the load resistor from the load terminals, and which can be simply short circuited. And whatever the current flows through this terminal, so that current is simply called short circuit current, and also called as the Norton's current, that is IN. So how do we get the IN value means? Simply we need to calculate the overall current of the network by using the network reduction technique. First we would like to determine the total current of the circuit, that is I total. So that is I total equal to the V total by R equivalent. So based on this one, we need to find out the I total of the circuit. So based on this one, we need to find out the I total of the circuit. So this is the I total that equal to the V by R equivalent. So from this one, we need to get the total current of the network. So based on this one, whatever the current flows through this path, that we need to find out based on this current. So for that we need to do the ratio of the total voltage of the circuit upon the R equivalent. So how can we get the R equivalent means, in anywhere we have to add the word the equivalent resistance of the any complex circuit. First we would like to determine the series and parallel combination of the elements. So that we will determine based on the flow of current given by the source. So this is the current flows to the network that is given by the source. So the current is moving towards this path and also enter here and divide between these two. So whatever the elements are, divide the current, those two are in parallel, and the combination is in series to this element. So in this circuit, the equivalent resistance, that should be the equivalent resistance, that is R equivalent equal to the, so that is a R2, that is a R2 parallel to R3, and which in series to R1. The same thing we have also taken here. So this is the R equivalent of the above network, and the total current we have to get based on this ratio, that is the total voltage upon the, so the equivalent resistance. So from that we got the exactly total current of the circuits. So based on that one, we can apply the current division rule, and we will get the, so exactly current flows to the, so required path, that is the short circuit path. So whatever the current flows to the short circuit path, that is called simply Norton's current, or also called as the short circuit current. So this is ISC. So this ISC, how can we get means, we can apply the current to division rule. Apply current to, so division rule. So based on the current division rule, so we can get the ISC values. So that is the total current of the network into opposite resistance by, that is the total resistance. I mean, we need to find out the current through this branch, that is the R2 element, that is none other than the R2 elements. The total current of the circuit, that is I total, we have determined based on this one. So that is something value we got. So based on the real values, we will get the different values. So that is Vs upon the R equivalent. This is the R equivalent of the circuit. And from this one, we need to find out the short circuit current, that is ISC or IN equal to, so total current of the circuit into, so that is a opposite resistance, opposite resistance divided by the total resistance, opposite resistance divided by the total resistance. So this is the total current of the circuit, and this is the opposite resistance, means the current flows through the R2 is the required value, then the opposite of R2 is the R3. This is the opposite element divided by the total element. So this is the way to get the Norton's current value. So now in the equivalent circuit, we have already gone through the IN, and the remaining parameter is the RN. So that's why the next procedure we need to get the RN. This one we have already gone, I mean we have already calculated. Then we need to get the RN with the required procedure. So the RN procedure means RN nothing but, I mean Norton's resistance also same as the Thevenin resistance, which means the procedure of the Norton resistance is also same as the Thevenin resistance. So how can we get the Thevenin or Norton resistance means, so in any kind of complex network, so to get the RN or R Thevenin, simply we need to remove or deactivate the energy sources present over the network. So if it is a voltage source, the network having, if it is a voltage source, we can simply, that is short circuit. If it is a current source, we can simply replace it by the open circuit. Actually, it's not the procedure. So if it is a voltage source present in the network, we can simply deactivate and replace it by their internal resistance actually. So their internal resistance. So if it is a idle source, so it doesn't have any internal resistance, that's why we can simply replace their the open terminals are by the short circuit. So here also same. If it is a current source present in the network while calculating the RN or RTH, so we can simply remove or deactivate that, and we can replace it. The terminals are by their internal resistance. So the ideal current source internal resistance should be infinite. That's why we can simply replace it by, that is open circuit terminal or open circuit path. So that is a procedure to get the RN or RTH. RN and also the RTH are both are same. So the procedure and also the calculation, the thing also same only. So how can we get the RN or RTH means? So whatever the network present in the whatever the elements are present in the network, whatever the sources are present in the network, we can simply deactivate all kinds of energy sources and also remove the load resistor from the load terminals. So the load terminals are keep as is and the energy sources are deactivated. Then, so for the above example, we got the circuit like this. We have removed the voltage source, and which can simply replaced by the short circuit, that is, so the remaining network is going to be appear like this. So based on this one, we need to find out the equivalent resistance of the circuit. So how can we get the equivalent resistance means? So here we need to analyze the series and parallel combination from this side, and also the reduce the complexity of network from the this side. This is the closed side. So based on this one, the R1 and R3s are parallel, and the combination is in series to R2. So how can I say like this means, if you need to assume a dummy source or ghost source for this open side, then the current is delivered by some dummy source. So this is a dummy source. So based on this current, the current is circulating so towards the R2 and enter here and divide between these two. So based on this one, the R1 and R3s are divide the current. So that R1 and R3s are in parallel, and the combination is series to R2. Hence, the equivalent resistance of the circuit should be like this: R1 into R3 upon R1 plus R2, because these two are parallel. That's why. So the equivalent value of this one is, we will get like this. So this is R equivalent of the above circuit. Also we can say R Norton or R Thevenin, both are same. So which equal to the R2 plus, so R1 into R3 divided by the R1 plus R2. So this is the procedure to get the Norton's resistance. So this is the procedure to get the Norton resistance. So then from the equivalent circuit, so this one we have done, that is IN we have already calculated for any network. I mean the procedure to get the IN value. So we have already finished it, and also we have determined the RN. There is a separate procedure to get the RN. So that is also we have done. So then based on this parameter, we need to draw the equivalent circuit for the complex network. This is the network we have taken. So for this one, based on the Norton's theorem procedure, we can simply replace the whole network by the Norton's equivalent circuit. So that is this one. Means using the Norton's parameter, that is a IN and RN. So we need to draw the equivalent circuit. So that is, this is the single current source, and which is in parallel to a single resistance. So that corresponding resistance is called R Norton, and the current source is known as I Norton. So in the starting of the this procedure, we have removed the load resistor. So we did not consider that. Then we can simply connect that load resistor at this load terminals. So based on this one, we need to find out the required load parameter, that is IL and as well as VL. We can find IL and VL values we need to find based on the required procedure. So first we need to find out the current through load resistor. This is the IL value. So otherwise this is the IL value. So IL, how can we get the IL? Means here this is a parallel network. Again we can use the current to division rule. Apply the current to division rule. So to the Norton's equivalent circuits, we will get the IL value. So that equal to the total current of the circuit into opposite resistance upon, so total resistance, opposite resistance upon the total resistance of the, so that division elements. So this is the I total. I total is none other than that is a short circuit current only. I mean this current only, or Norton's current only. Then the opposite resistance of this one is, so we need to calculate the current through this element. Then the opposite is this element. So whatever the elements are dividing the current, so that elements are considered as sometimes this one is opposite and sometimes this one is opposite. If you need to get the current through this element, then this element is the opposite. So we require to get the current through load resistor. That's why the opposite of the load resistor is a R internal. That means the Thevenin resistance or Norton resistance. That is this one. So this is R internal or R Norton. We can also say it is R Norton divided by the R Norton into RL. So we need to rewrite that one. That is IN equal to the IL equal to the IN into RN divided by the RN plus RL. So this is the procedure to get the load current value by using the Norton's theorem. So similarly, we can also get the voltage across the load resistor, that is VL equal to the IL into RL. So based on this formula, we can use, we can get the Norton's current value. So IL values, again we need to substitute the same only, IN into Rn divided by Rn plus RL. So into Rn key capacities. Sorry, into RL key capacities. So this is the procedure to get the RL value. So this is the Norton's theorem equivalent circuit. The summary of the session. So in this session, till now we have discussed about what is Norton's theorem. So Norton's theorem statement and what kind of procedure involved in the Norton's theorem. So that we have discussed till now. And in the Norton's theorem, so any kind of complex network we can simply replace it. So that whole network into the simple Norton's equivalent or simple equivalent circuit. So that has the single current source. So that current source is called IN, and which parallel to the single resistance, that's called RN. So this is the network. So came from the Norton's theorem procedure. So any kind of complex circuit, that is that kind of circuit having more number of active elements, that nothing but voltage sources, different voltage sources and different current sources. So we can simply replace the whole network into this single source network. So by this we will get the required parameter easily. And also we gone through in the Norton's theorem procedure to the Rn value. How can we get the Rn value and how can we get the IN value? So there is a different procedure to get these two parameters. That is IN. How will we get the IN value from any kind of component network? Means we can simply deactivate or remove the load resistor from the load terminals, and whose terminals are simply keep short circuit. So then we will get the corresponding short circuit path current is called Norton's current. Then what about the Rn? Rn means Rn, that is a Norton resistance. There is no separate procedure to get the Rn and also the RTH. Both are same only. So while calculating the Norton resistance or Thevenin resistance, we can simply deactivate all kinds of energy sources and also remove the load resistor. And whatever the terminals are open, we can calculate the resistance from the terminals, and the remainings are closed. So then based on that one, we will get the R Nortons. The last thing is, that is the applications of the Norton's theorem. So that is the applications of the Norton's theorem. So by using the Norton's theorem, we need to design electronic circuits, like electronic circuits, that is filters. So filters, amplifiers, etc. This is the one application, and also used in electrical machines, and also used in power system, electrical power system. So these are so many applications are there for Norton's theorem. So this is the end of the session, and so this is the complete discussion about the Norton's theorem, and we will discuss the numerical based on the Norton's theorem and also Thevenin's theorem that we have already covered in the last session. So this is the end of the session. Thank you, Varner.